Let's talk about the complication. The big complication with follow-up tests or post-hoc tests after ANOVA is called the multiple comparison problem. So doing post-hoc tests are kind of like going fishing for differences, right? The omnibus tells you something here is different. I don't know what. And then post-hoc tests are like going fishing to find out what's different from what. And the key problem with that is that we end up testing many hypotheses using the same data. And remember that table I showed you here. There are 7 different alternate sort of scenarios that could emerge. And by doing each of these 3 tests, we're essentially retesting the same data multiple times. And it turns out when you do that, when you test many different hypotheses using the same data, your type 1 errors accumulate. Remember what a type 1 error is? It's an error you make where you declare there's a difference where there actually isn't. Right? You declare the null hypothesis should be rejected when in fact it's true, and the difference is just due to random sampling. So it turns out if you keep testing after an omnibus test, let's test these, let's test those, let's test those, and you test every possible scenario. Each individual test, the type 1 error rate is 0.05. Right? If you're using 0.05 to make your decision about whether to reject the null or accept it, then each individual test, your risk of a type 1 error is your alpha level, 5%. But what's called the family-wise error rate, the chance of making a type 1 error overall goes up. It gets inflated. So type 1 error is when the null hypothesis is true and you reject it. But it was true, so that's an error. Right? If the null hypothesis is true and you fail to reject it, that's a correct decision. And the probability of making a type 1 error is your alpha level. You get to decide that, right? It's not based on your data. It's not based on the p-value. What's related to the decision. But whether or not you reject the null hypothesis or not is based on where you draw that line in the sand, 0.05, and nothing else. We'll talk about these other things in a minute. So you set your threshold for rejecting the null hypothesis. A lot of the time it's set at 0.05. In some subfields of science and some labs, you might find 0.01 is what people strive for instead. But it's basically the proportion of time you're willing to make an oopsie and erroneously say there's a difference when there actually isn't. So I wanted to show you some simulations in R that illustrate this, and the code is posted on the slides. So you should try it out, if not right now, later, because it's instructive. It seems counterintuitive what happens, but it's instructive. What we're going to do is we're going to assume the null hypothesis is true. We're going to simulate a universe where the null hypothesis is true, and we're going to take 3 samples of size 10 from the same population with the same mean, right? And because of random sampling, each of our samples is going to have a slightly different mean. We're going to conduct a one-way ANOVA on those 3 groups, and we're going to store the F statistic and the p-value, and we're going to store what decision we make, reject the null or don't reject the null. We're going to do 10,000 of those simulated experiments because we can. Computers don't complain about work. And we're going to count out how many times we ended up making the wrong decision. Right? We know the null hypothesis is true because we're making it true in our simulated universe. And we're going to count out how many times we make it true. That's a little small on the slide, on the screen, but you can see it on your own machine. And I'm going to put my computer there. Let's put it here. Okay, so that work. HDMI. Oh, there. Okay. There's my laptop. There's the same code that's in there. And basically the way it works is we're setting the sample size to 10,000 simulated experiments. We're going to initialize some arrays to store our p-values and our f-values and our precision. And then we have a loop. I haven't talked about what a for loop is, and I'm not. You can kind of see what the idea is. It repeats code a certain number of times. So we're going to repeat the code in the for loop 10,000 times. We're going to sample from a normal distribution with mean 0 and standard deviation 1, n samples, n is 10, and store those in y1. Then we're going to sample another group and store them in y2. And then we're going to sample another group and store them in y3. So that's randomly sampling values from a normal distribution with the same mean, and just storing them in 3 different variables, y1, y2, and y3. Then we're going to concatenate those together in a list. We're going to make a factor. Their codes group 1, group 2, and group 3. And we're going to put all that in a tibble, a data frame. Then we're going to do an ANOVA, a one-way ANOVA, on those 3 groups. We're going to get the summary of that ANOVA, and we're going to extract from it the p-value and the f-value. This is ugly code here, which is necessary to extract those p-values. Then we're going to compare. If the p-value is less than our alpha, 0.05, then our decision is reject. Otherwise, our decision is accept. So even if you don't quite get the code specifically, you get the idea. We're randomly sampling 3 groups from the same distribution, so null hypothesis is true. We're doing a one-way ANOVA. We're getting the f and the p. We're comparing the p-value to 0.05, and then we're making a decision and storing it that way. All right, let's do that. Boom, 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 boom. Okay, doing 10,000 of them. There, it's done. Let's look at the result. So there's my tibble, 10,000 experiments by 3 rows. I have all my p-values for each of the 10,000 experiments, all the f-values, and all my decisions. Good, the first 10 I didn't make a mistake. I accepted the null, which is true, right? But you can see the p-values vary. Sometimes the p-value is really high, which is what it should be. Sometimes it gets pretty low, 0.1. And if we look lower in that data frame, the other 9,990 values, we would find some cases where the p-value was less than 0.05. Not because there really is a difference in the populations, right? It's one population. But because of random sampling, we just happened to pick 10 values that were big in one group compared to the others. So now, let's make a plot. Here's the plot of all of the F statistics in those 10,000 experiments. So on the bottom is the value of F, and on the top is the count. And that red line represents 5% of the F values. And so what you see about the F statistic under the null is it's bunched near 0, right? The vast majority of F statistics, when the null hypothesis is true, the vast majority of F values are really small, close to 0. Close to 1, actually, but bunched up towards the bottom. But there are some naughty little F values that are really big. Like there's one that's 10, right? An F value of 10 indicates a really big difference between groups. And that was a really unlucky random sampling, right? The null hypothesis is still true. That would be a type 1 error. Now let's look at the p-values. And this is the thing that surprises even me still. It took me a while to accept that this is true. But that's the distribution of p-values under the null hypothesis. You would think maybe they'd be bunched up near 1, right? And there'd be very few significant p-values. But it's not true. Under the null hypothesis, the distribution of p-values is a uniform distribution. Every p-value is equally likely. I know, it's crazy. It doesn't feel right, right? It feels like somehow really wrong. But I encourage you to play with the code because it's true. It kind of goes up and down here because it's only 10,000 experiments. If I made it 10 million, it would be much smoother. or if I increase the bin of that histogram, it will be smoother. But the truth is, every p-value is equally likely if the null hypothesis is true. So think about it this way, just slightly pessimistic. You're going to do your undergrad thesis once, not 10,000 times. Right? You're going to do it once. And if the null hypothesis is true, then when you do your thesis experiment once, it's like putting your hand in a bucket of those 10,000 p-values. Everyone is equally likely, and you pick out one. Just one, right? Which one are you going to pick? Maybe you'll pick one of these, right? And that'll incorrectly tell you that there's a difference when there really isn't. So that red line is at 0.05. Now let's count. How many times did I end up rejecting the null hypothesis? I ended up rejecting, in those 10,000 simulations, I rejected the null hypothesis 505 times, which is 0.0505, right? Not quite exactly 0.05, but again, if I did 10 million instead of 10,000, it will be even closer to 0.05. So is it a coincidence that I made a type 1 error 5% of the time? No. So what determined that? Yeah.
Setting the alpha level at 0.05 when we first ran the simulation.
That's right. What determined how many type 1 errors I made was the alpha level. And where's the alpha level in this simulation code? It's right here. If p is less than 0.05, right? That's the part of the simulation where the experimenter's brain comes in, right? That's you as the experimenter looking at your p-value and saying, what should I do? I should reject the null, right? That's not based on some feature of the data or the sample size or anything. That's just you as the experimenter deciding one thing or another. So if I change that to 0.01, and I rerun that simulation. Okay, just a second. There. Now how many type 1 errors did I make? Whoops. Now I made 109.01 type 1 errors. Exactly what I set my alpha to. Yeah.
Could we think about it making sense? Because we learned that, like, if the null hypothesis is true, that means there's no, like we assume that there's no relation or no impact. So that would mean any game is equally likely. Because if they're randomly, like, by chance, kind of sorted, then it doesn't really matter.
Yeah, that's a good way of thinking about it. If the null hypothesis is true, then any difference between groups is equally likely under random sampling. Right? You could get group 1 bigger than group 2, or group 2 bigger than group 1, a little bit or a lot. Every scenario is equally likely. That's right. Yeah.
I have a question about the F value you were mentioning.
Yeah.
So, like, with the F distribution, I think, like, conceptually, like, we've been told that, like, the mean, it kind of revolves around 1, right?
That's right.
But, like, considering the F value ratio, it's like between, like, the variance between groups divided by, like, the within groups, right? Like, the error essentially of, like, that mean being different, right? Now, considering that it's under our null hypothesis, wouldn't that mean that essentially we would be thinking that between groups there would be, like, 0 variance at all? So why is it that you guys are at 0 exactly?
On average, the difference between groups should be 0. That's right. And so you're asking why is the average of F 0 itself? Yeah, that's a good question. I think it's because the F statistic is not symmetric around 0. You can't have a negative F. And so when you sort of flip the negative onto the positive, you end up with an average that can't be 0. If that makes any sense. Like the difference between groups can be this way or that way, right? And for the F statistic, both of those count as a positive. If you were to plot the distribution of just differences between means, then it would be an average of 0 and it would be symmetric around 0. So So the point of showing you the simulation was first to give you the code so you can play with it and convince yourself that this is true. But mainly to drive home the point that, that's the F distribution under the null, and that's the E distribution. Then the distribution is flat under the null, every possible p-value is equally likely. And the second thing is that what determines how many type 1 errors you make, if the null hypothesis is true, it's nothing to do with your experiment, it's just you. It's your brain. It's what you decide to do with that p-value. Right? You'll get under the null any p-value under that whole distribution is equally likely. But it's what you decide to do with it that determines how many type 1 errors you make. So if you're okay making 1 in 20, 0.05, then you set your threshold of 0.05. If that makes you uncomfortable, if you want to be more stringent, then set it to 0.01. Then you only make a type 1 error 1% of the time. All right, let's put the screen back. So we get to choose our type 1 error rate when the null hypothesis is true. When the null hypothesis is actually false, right? That's the other universe that's possible. The null hypothesis is false. Then we want to reject the null hypothesis. That's what we want to do. We want to reject it. If we fail to reject it, then that is a type 2 error. That would be when we get a p-value that's above 0.05 and we say, no, I can't reject the null hypothesis, when in fact it's true. Right? The drug actually works, but in your experiment, your p-value was above 0.05 and you weren't able to say the drug works. You're like, it could have been like this if it didn't work. So that would be a type 2 error. And what determines the probability of a type 2 error is a quantity called beta. So alpha is the probability of your type 1 error, and beta is the probability of your type 2 error. What is beta? Beta is 1 minus power, or power equals 1 minus beta. And what's power? Power means statistical power. It refers to the likelihood in your experimental design that you will correctly detect an effect when it's there. So it's the probability of correctly rejecting the null when the null is in fact false. Or the probability that you will correctly detect the difference when there actually is one. And whereas alpha is the only thing that determines the probability of the type 1 error, there's a whole bunch of things that can affect the probability of a type 2 error. There's a whole bunch of things that can influence the power of your experiment. So the effect size can determine the power of your experiment. If you're attempting to detect a difference in blood pressure with some drug, then if you give a bigger dosage of the drug to get a bigger difference in blood pressure, you're more likely to detect that than if you give a small dose of drug and just have a small difference in blood pressure. So that the size of the difference itself determines the power to detect it. The sample size also affects the power to detect the difference. Larger samples give you more statistical power to detect the difference. Why? What's the concept behind that? I mean, there's a mathematical reason why a bigger n gives you more power, right? It's because then you have more degrees of freedom left over. And remember, the denominator of the f has the leftover degrees of freedom in it. And so if there's a bigger number in the bottom, it means f is bigger. That's the mathematical reason why. So what's the conceptual reason? Why would a bigger sample size afford you more power to detect a difference? Yeah?
It's because it's more robust, so it's less likely to be affected to random sampling.
Yeah, what you said is it's more robust and it's less likely to be affected by random sampling. It's a good way of putting it. I would also put it like this, that the concept is that bigger samples give you better estimates of the actual true population situation, right? Imagine you did an experiment and you measured everyone on planet Earth except one person, right? Then you have the entire population except just one, right? That would give you a really good estimate of the population, because all you're missing is one person. And that one person is probably not going to swing your estimate wildly in any one direction. And as you reduce the size of that sample, you're going to get a worse and worse estimate of the true population value. Or to put it differently, all of the leftover people that you're not sampling, that you're not including, they could sway the value of your estimate one way or the other, more and more and more, all the way down to the extreme where if I want to measure the average height of human adults, then I'm like, well, I'm a human adult, I'll measure me. A sample size is 1. I'll get an estimate, but it's not a very good one, right? Because it hasn't taken into account the variation in the population. Only if I went to like the Netherlands would people be installed on me. I did that once with my wife years ago. She's like, it was terrible. We were in the airport, it was crowded, and I couldn't find you. Like, normally I can see you because you're like a little bit above everyone, but in Amsterdam, it was like I was average height. So, the other thing that can affect power is alpha, right? Alpha affects your type 1 error rate when the null hypothesis is true. When the null hypothesis is false, the alpha level will also affect your statistical power. If you set your cutoff from when you declare significance to be really low, like let's imagine you made it 0.001, right? You would make very few type 1 errors when the null hypothesis is true, so that's a good thing. But you'd also make many more type 2 errors when the null hypothesis is false, because you require your p-value to be really small to declare that the null hypothesis should be rejected. So the alpha level affects both universes, right? The universe where the null hypothesis is true and the universe where the null hypothesis is false. So there are functions in R that will take these things into account and compute for you what your statistical power is under a given scenario. There's one called power.ANOVA.test that will do it for an ANOVA. There's one called power.t.test that will do it for a t-test. And they're always under the assumption that the null hypothesis is false. So here's a little example. Let's say we have an experiment with 3 groups. And let's say our goal is we want our statistical power to be 0.8, which means that if the null hypothesis is false, we want to make sure we reject the null at least 80% of the time. So we would call power.ANOVA.test. We would set groups to 3. We would set our desired power to 0.8. And then we also have to give it some more information. We have to give it some information about the effect size. We have to say, what do we expect the differences between groups to be? And what do we expect the differences within groups to be? What do we expect the distance between those peaks in the distribution to be? And what do we expect the width of each of those distributions to be? So to do this power calculation, we need some estimate of the effect size, both the difference between means and also the variability within each group. And that's not easy to come by necessarily. You can do it by looking at previous literature where people have done similar experiments to get a guess. You can use a pilot study in your own lab, do a small version of your experiment to try to estimate these things. But you need them to do this power analysis. So in this case, we're going to set the between groups variance to 1 and the within groups variance to 4. That basically says we expect the within groups variance to be 4 times as big as the between groups variance. And when that's true, it will spit out n equals 20.30205. And since we can't take 0.3 of a person, we can round down and say we would need 20 people in each group with that scenario to get a power of 0.8. And if you want a power of 0.9, you can redo that function and set a power to 0.9, and it would say, well, you need, I don't know what it would say. 29 people or 35 people per group to get a power of 0.9. So it's a really powerful way of getting a quantitative estimate, a principled way of estimating both what sample size should you have in your experiment, and retrospectively, if you have an experiment with a certain sample size, what statistical power do you have to detect the difference if it's there? You don't want to run your thesis experiment with low statistical power, right? That's just starting with, 1 foot in the grave. It's like, if you're running an experiment with really low power, it's basically saying, well, even if there is a difference, I'll only be able to detect it, 10% of the time. Ugh, what a horrible thing to do to yourself, right? You want an experiment with the highest statistical power you can manage. And the good news is, some of these things are under your control. Sample size is usually under your control. We're all lazy, we don't want to collect more data necessarily, but more data always gets you closer to the truth. Our alpha level, we probably don't want to mess with that too much. We don't want to put it above 0.05, that's for sure. Effect size, that may or may not be under our control. We may be able to control the expected difference between means. Right in that drug example, we're doing a study on mood or blood pressure or whatever it is. Use a bigger drug dosage to get a bigger difference if it's safe to do, if it makes sense. And then the other part of effect size, right? The top of effect size is the difference. The bottom of that fraction is some metric of the within group variability. And so that might be under your control as well. When you're running your experiment, anything you can do to reduce the variability of your data within each group, the better off you'll be. So excluding outliers from your data set. If you're testing humans, and it's a long, boring experiment, like, in visual psychophysics, where you have these 2-hour experiments in a dark room where you're trying to detect tiny dots, it can be very boring. Give your participants a break. That will reduce the variability of the responses. So anything you can do to maximize the difference between groups and minimize the within-group variance will also affect your power. And the good news is, if you nudge multiple factors just a little bit, you get a big boost in statistical power. And you can play with this calculation, this function, and sort of see how that works. Yeah, we talked about that. So how are we doing for time? We're almost at an hour. So why don't we take a small break? Let's say 10 minutes, and then we'll come back and we'll talk about multiple comparisons again.